So what we did yesterday is we tried to represent a direct lattice using reciprocal lattice constants. We defined what is a reciprocal lattice and how the reciprocal lattice constants are related to direct lattice constants ABC. So now we will try to see how Bragg's law is applicable to this reciprocal lattice and how that helps us in understanding the phenomena of diffraction. See, what is drawn here, I didn't want to draw it, and these two image pictures or these two drawings are directly taken from Stout and Jensen's textbook. So I have a photocopy of that, I'll give you that. So today you don't need to draw these things now, let us try to understand. So what is represented here as that grid line represents the A star C star plane of reciprocal lattice. So all the points of intersections are reciprocal lattice points in A star C star plane. Instead of A and C plane, I am saying it is A star C star plane. So in that plane, you have those points in a given array. Now, we use one such point which falls here as the reciprocal lattice origin, and then I am trying to draw a circle like this in such a way that reciprocal lattice origin falls at the circumference and the radius of that circle is 1 by lambda, which means this radius depends on the wavelength of radiation that is used. Whether we use copper or molybdenum, the size of this circle will change. So now, when I have drawn such a circle with reciprocal lattice origin here, we see that some points, like this point P, falls on the circumference of the circle. Not all points fall on the circumference of the circle. Some points exactly meet the circumference, some points are very close to the circumference. This one is meeting, but not that or some other point. So now we assume that the X-ray beam that I am using is in the plane of that A star C star lattice. The beam is not perpendicular to that A star C star plane, it is in the plane of the lattice, the A star C star plane. So now if I see that this direction is the beam direction of the beam, and I find that this particular point is at the circumference. So I am now drawing a triangle from BPO inside the circle. This same figure is drawn here without the grid now. You see, there is a plane which is like that this direction is giving you a particular plane. And from this point to that point, this is the distance between two sets of parallel planes. So what is that distance in reciprocal space? 1 by dHk. If the particular point P represents a plane HKL in the direct lattice, this P is the reciprocal lattice point corresponding to a plane HKL. So the distance from O to P is nothing but 1 by dHk. So now if we look at this diagram, X-ray beam falls from that plane at angle theta, and it should diffract in the direction of OD. So this would be the diffraction direction, which is then parallel to the direction CP, because this angle, when it is 2 theta, this angle is also 2 theta. So this will be the direction of X-ray diffraction. So now if we look at the particular triangle OPB, that is OPB, this is right angle triangle. If this is theta, that angle is also theta. Now if we try to see what is sine OBP, sine OBP. So what is sine OBP? OP by OB? OP by OB. What is OP? 1 by DHK. What is OB? The diameter of the circle. What is the radius of the circle? 1 by lambda. So diameter of the circle is 2 by lambda. So I have put OP by 2 by lambda. And then I am changing that sine OBP as sine theta. And rearranging it as OP by 2 into lambda. So now P being the reciprocal lattice point, we can replace OP by 1 by DHKL. So if you put OP equal to 1 by DHKL, it simply becomes lambda by 2 DHKL. So on rearrangement, it is nothing but Bragg's law. What do we get to know from this? We get to know from this that if we draw a circle of radius 1 by lambda, taking the crystal as the center, and the corresponding reciprocal lattice is drawn with respect to the crystal position, then any point which falls on the circumference of that circle meets Bragg's condition and gives you diffraction. No other point gives you diffraction. So, if I place my crystal at point C, static, I have A star C star like this, maybe A star B star like that, and B star C star like this. So, 3 different sets of orientations. So, now instead of thinking that this is a circle, if we assume that it is a sphere of 1 by lambda radius, so all the points around the crystal which falls in the circumference of a sphere of radius 1 by lambda will satisfy that condition and will cause diffraction. So by expanding this circle into a sphere, we can think of that if I have a crystal here, there is an imaginary circle around it, or sphere around it rather. That imaginary sphere corresponds to a set of reciprocal lattice points which is on the circumference. Of course, there are reciprocal lattice points everywhere in the sphere, but those will not cause diffraction. Until and unless one reciprocal lattice point falls on the circumference of the sphere, it does not cause diffraction. So now you can easily understand, if I have a mechanism to rotate the crystal, if I am able to rotate the crystal about its axis, suppose I mounted the crystal in such a way that B star is that direction and this plane is my A star C star plane. If I rotate it, what I am going to rotate is this grid. If I rotate this grid, at some point this reciprocal lattice point which is inside will cross somewhere here, will cause diffraction. If something is here, at some point will cross this region, will cross diffraction in a different direction. So all the points which are there in this diagram, all the point of intersections by rotation of the crystal can be made to pass through the circumference of the sphere that we are constructing, assuming the wavelength is lambda. So now we can have different wavelengths. If lambda is large, suppose for copper, 1 by lambda is small, so the radius of the sphere is small. So if I use a large wavelength, I have only a very small sphere. So only a much smaller number of reciprocal lattice points can be made to pass through this small sphere. Whereas if I use molybdenum radiation or silver radiation, which are much smaller in wavelength, what is wavelength of copper? Approximately 1.54. Molybdenum is 0.71. Silver is 0.68. Just let me tell it. I think it is 0.58. So it is so small that the sphere becomes much larger. When the sphere becomes much larger, immediately your conclusion is I can access larger number of reciprocal lattice points. How the position of reciprocal lattice point is related to resolution? Smaller the d value, larger is 1 by d, further is that reciprocal lattice point from origin. That means for a particular lattice, if you keep on chopping thinner slice with smaller wavelength, you can go to much thinner slice, much thinner d values. Because 1 by d is large and that large d value can be accessed by the larger sphere that we have considered here, that is the short lambda sphere. Short lambda means smaller wavelength sphere. Smaller wavelength sphere is larger, so you can access more number of reflections, more d values which are smaller and smaller and smaller. Now the question is, which reciprocal lattice points can be passed through these spheres? Are those only the ones which are very close to that? Is there any restriction on that? Or those should be only inside the points, but inside the sphere? What is your answer? Which are the reciprocal lattice points that can be made to pass through the circumference of this circle? Is it only those which comes inside during rotation, or the ones which are at some distance from here, or anything? The answer is here. The sphere that we are talking about is this one, of radius 1 by lambda, diameter 2 by lambda. So when a reciprocal lattice point is passing through that sphere, it causes diffraction. Now, taking that as a circumference and this as the center, if I draw another sphere of radius 2 by lambda, I get something called a limiting sphere. Geometrically, all the reciprocal lattice points which fall within that sphere of radius 2 by lambda, by rotation of the crystal which is placed here, can be made to pass through that sphere. The ones which are outside this sphere cannot be made to pass through that sphere. Right? If I rotate the crystal in this plane, whatever planes are there, whatever directions of reciprocal lattice are there, in that particular plane which is inside this sphere can pass through that sphere. Outside, no. So this particular smaller sphere is called the sphere of reflection, and that one is called the limiting sphere of reflection. So limiting sphere is a larger sphere which can be accessed. The reflections falling in the limiting sphere can be accessed and can be recorded, provided when they pass through the sphere of radius 1 by lambda. Right? So this concept was introduced by Peter Ewald, and the sphere of reflection is called Ewald sphere after the name of Peter Ewald. So let us see one video. Hopefully the internet works here. Faculty internet works, right?